7.1, graph exponential growth functions. This illustration shows what we're going to be talking about today. Here is the savings with no compound interest. Here is the savings with compound interest. Clearly, there's something about compound interest that we like, and we'll be learning about that in this lesson. Let's start by understanding what an exponential function is. It is a function of the form y equals ab to the x power. So you'll notice here that this is the first time we're seeing x in the power. In this case, we have to say that a does not equal 0, because if a was 0, then we would just have y equals 0. And also, b is a positive number, but b does not equal 1. And why do I have to say b does not equal 1? Well, if b were 1, then we would have 1 to the x power. 1 to the any power is just 1. And so if b were 1, we would just have y equals a, which is not exponential. So that's why I have to exclude those two cases. But in general, exponential function of the form y equals ab to the x, if both a is positive and b is a number bigger than 1, meaning in this case b is not a fraction, because remember b has to be positive. So if that's true, then we have an exponential growth function. And the growth factor is just that b. Now, I just wanted to introduce you to the term asymptote. This comic right here is just something funny about asymptotes that I'm going to explain in a moment, but I just want you to know this graphic here is not what we're talking about today. But an asymptote is just a line that a graph approaches more and more closely. So it gets closer and closer and closer to the asymptote. In this comic here, it's saying the man's going along, no touching, because a vertical asymptote actually cannot be crossed, but we will also have horizontal asymptotes, which is what I'm talking about in this lesson. Okay, and this graph, this means it's getting closer and closer and closer to this line here, this line which is y equals 0. It gets closer and closer and closer to that line as the x values approach negative infinity. So again, this illustration is just funny because it says you can get close but no touching, and so that might help you remember what an asymptote is. But let me just make it clear that you can cross a horizontal asymptote. Hopefully now you've come to expect that we're going to talk about the parent function first, and then we're going to do some transformations of it. So we're going to start with the simplest case, y equals b to the x. So now we're just letting a equal 1. And in this case, we're going to first look where b is greater than 1. So just note that b is not a fraction in this example here. The most basic case looks like this. We could plot some points. If we put in a 0 for x, b to the 0 power, anything to the 0 power is just 1. And if you put in a 1 for the x, b to the first power is just b. So basically what I did was I made a table of values. F of x equals b to the x power. And when I put in a 0, well, b to the 0 power is 1. And when I put a 1 in, well, b to the first power is just b. And so those are the 2 points that were plotted. And then we know that our graph looks like this because we know it's exponential growth. And you'll get used to this. The x values it takes in are all real numbers. There are no restrictions on our domain. However, our range does have a restriction. We see that only values greater than 0 are being plotted. Why greater than 0? Our asymptote for exponential growth functions is y equals 0. So in this case, our graph gets real close to y equals 0, but it never actually touches it. Let's try graphing y equals 3 to the x power. Let's just start with the table of values. Let's just put in -1, 0, 1, and 2, and let's see what we get out. When we do 3 to the -1 power, well, we know now that is 1/3. When we do 3 to the 0 power, we get 1. 3 to the first power is just 3. And then 3 squared is 9. So we put in a -1, we get out a 1/3. We put in a 0, we get out a 1. We put in a 1, we get out a 3. And we put in a 2, and we get out a 9. Because we really haven't shifted this thing up or over any, we will just assume that our same horizontal asymptote is at y equals 0, and so our graph will look like this. And the reason we know this is just because we see that it's of the form y equals ab to the x. And so we're going to start knowing that these are exponential growth functions. Again, note that the x is in the power. When we go to graph this function, we probably realize that this just means that we have a vertical shrink by a factor of 1/3. So we can take the same points that we had in our previous example, -1, 1/3. When we put in a 0, we got out a 1. When we put in a 1, we got out a 3. 2, 9, and now we'll just do a third of that. A third of 1/3 is a 9th. A third of 1 is a third. A third of 3 is just 1, and a third of 9 is just 3. And you could have just put them originally into this function. You would have gotten the same points here. It's very important to note that this is the a in y equals ab to the x, and the a is our vertical shrink or our vertical stretch. So we can go ahead and plot these. And it's going to look a lot like the other one did. It's just going to be vertically shrunk, but we're still not going to cross that y equals 0 line. In this problem here, this 3/2 is actually our b, so it is not representing a vertical shrink or stretch. This negative, however, does indicate that we are reflecting over the x-axis. So let's just go ahead and make a table of values. Let's start with -1, 0, 1, and 2. When I do -3/2 to the -1, well, 3/2 to the -1 just flips it over, and then I have a negative out in front. So again, I applied the -1 power first. PEMDAS, you must do the exponents first, and then I just put the opposite in front. When I do 3/2 to the 0 power, or -3/2 to the 0 power, I get -1. Anything to the 0 power is 1, and then I apply the negative last. -3/2 to the first power is just -3/2. -3/2 squared. Must do the exponents first, so I get 9/4. 3/2 times 3/2 is 9/4, and then apply the negative. So let me just plot those. Notice that I have reflected this over the x-axis. And that's what my graph looks like there. Oh, now we get into the fun. Now we have, first step is a vertical stretch by a factor of 2. Our second step is going to be a horizontal shift. 2 units left. Because remember, by default, it's x minus. So when you have a plus, that means it's moving left. And our third step is going to be a vertical shift. 1 unit up. And so, the domain has not changed, even though I shifted it a little bit because the domain before was all real numbers. The domain is still going to be all real numbers. However, my range, remember before was just greater than 0. So now if I shift it 1 unit up, instead of being 0, it's going to be 0 plus 1. That's for the 1 unit up. In other words, our range is y is greater than 1. So I'm just going to draw a little dotted line here so I remember that that is my asymptote. I'm going to abbreviate it ASY, asymptote at y equals 1. So what I think I'm going to do in this case is just start with making a table of values for y equals 4 to the x power, and then I'm going to apply my transformations. So let's do -1, 0, 1, and 2. So when I have 4 to the x power, I have 4 to the -1, which is 1/4. When I have 4 to the 0 power, I have 1. When I have 4 to the first power, I have 4. When I have 4 to the second power, I have 16. So the first thing I'm going to do is I am going to multiply all the y's by 2 because that's my vertical stretch. So instead of 1/4, I will get 1/2. Instead of 1, I will get 2. Instead of 4, I will get 8. Instead of 16, I will get 32. The next thing I'm going to do is I am going to shift all of my x coordinates 2 units left. So instead of -1, I have -3. Instead of 0, I have -2. Instead of 1, I have -1. Instead of 2, I have 0. I shifted all the x's 2 units left. The third thing I'm going to do is I'm going to shift the y coordinates 1 unit up. So instead of 1/2, I get 1.5 or 3/2. Instead of 2, I get a 3. Instead of 8, I get a 9. Instead of 32, I get a 33. Again, the green was the vertical stretch. I must apply them 1, 2, 3. Vertical stretch, horizontal shift, vertical shift. Now let me just plot these new points. -3, 3/2. -2, 3. And -1, 9 is the last thing that I'm going to be able to fit here. So let me just draw that in. Again, be careful that you do not cross your horizontal asymptote, which was at y equals -1. The 3 things I'll be looking for on your test or quiz are that you do not cross the asymptote, that the general shape looks correct, so all of these should have a shape that looks something like what I've drawn, and the third thing is that you've plotted 3 points that are accurate. As we just talked about in the last example, when we want to graph something of the form y equals ab to the x minus h plus k, you begin with the parent function y equals ab to the x. The horizontal translation is just h units right. By default, you go right. So if it's a minus, you go right. A vertical translation of k units up. Again, by default, if there's a plus there, it goes up. Now we're going to talk about exponential growth models, which are of the form y equals a to the 1 plus r to the t power. So it's kind of like our b is 1 plus r in this case, and our x is just the t. And the t is just indicating over time. Now, when we do exponential growth models, we are going to be increasing by a fixed amount each year. No compounding yet. So we are going to be doing compounded growth. You can see from the first illustration on the comic on the front page that we like compounded growth in terms of our money growing, but right now we're going to start with something simpler just by increasing by a fixed amount each year. A in this model just means our initial amount that we put in. Maybe you're putting money in a bank account. A is your initial amount that you put in. R is the interest rate. So usually when you put your money in a bank, you get a certain interest rate. 1 plus R is a growth factor because think about it. Say we had $5, okay? And say that I earn 1% on my $5. How much do I have? I have 5 plus 1% of 5. In other words, I have 1 plus 0.01 of 5 if I factor the 5 out. So that's why I'm doing that 1 plus R times the initial amount. You see that? The 1 plus R is just the growth factor, and it's because you have to remember that you want to add your original amount plus the percent that you're getting. T is just your time, typically in years. Let's go ahead and try a problem. In 1970, the population of Kern County, California was about 333,000. From 1970 to 2000, the county population grew at an average annual rate of 2.4%. Write an exponential model giving the population P of Kern County T years after 1970. Remember, we had y equals a 1 plus r to the t power. So here the initial amount, A, was 333,000, and then we have 1 plus 2.4%, which is 0.024 to the t power. In other words, 333,000, and we can just do 1.024 t. About how many people lived in Kern County in 1990? Well, 1990 means that t is equal to 20, because remember, t is just years since 1970, and that would be 20 years after. And so we can just do p of 20, p after 20 years. And you can use your calculator to do this. Remember, to make the power, just use that little symbol like that, and we should get 530,000 people. Don't forget your units here. Estimate the year when the population of Kern County was about 400,000 using a graph. So basically what we want to say is when does P equal 400,000? When? What is T? So I put in all my other variables except for t. Now I get out my calculator. So let's go ahead and go to y equals, and in y1 let's put 333,000 times 1.024 to the x power. Even though we have a t power here in your calculator, just always use to the x power. And then we want to know when that equals 400,000. So we want to know when y1 and y2 intersect, pretty much. So before we go to graph this, we obviously know that our y is getting huge in this case. So let's play with our window so that we're going to be able to see something. Well, what does x represent? X represents our time. So you know that the x can't be less than 0. So let's make it less than 0, and let's just go up to 20 years. That's the year 1990, right? Always leave your scale at 1. For the y minimum, well, you know that the population can't be less than 0, so why don't we start at 0? And we want to go up to at least 400,000. Let's go a little bit above that. Let's go up to 420,000, and let's try that. Let's graph it. All right, and we see the intersection point right there, right? That's when the two lines, y2 is going to be equal to y1. That's what we want to find, where y2 equals y1. So let's go to second calc. There's also an intersect function there that we haven't used before, so intersect, that's number 5. And look, we have a slight problem because when we go to do this, we can't see what we're doing because the y equals covers it up. So let's go ahead and just adjust our window a little bit more. Instead of going to just 420,000, why don't we just go to 500,000? That's a bit bigger. We'll see a little bit more that's going on. All right, much better. Now my intersection point's here, and I don't think the words are going to be covering it up. Again, go to second calc. Number 5 is the intersect. We want to know where the two lines intersect. For this one, you're just going to use your left and right arrows like you did before to get real close to the point where you think is the intersection point. Once you get there, just press enter, and this time you're just going to press it 3 times because you're on the point pretty much as close as you can be. And so we get 7.73 about. So since we get t is about 7.73, well, what year would that be in? 7 point anything would already be in your 8th year, right? So it says estimate the year when it happened. It would have happened in 1978. Again, because it's 7 point something, it means you're already in your 8th year. And now we're getting to compound interest. Compound interest is of the equation A equals P times 1 plus R over N to the NT. So in this case, this N is just how many times we compound per year. So we compound N times per year. You'll see that the more times that you compound, the more your money grows. A is just the amount in the account after 2 years. P is the principal. In other words, the amount that you invested, the amount that you put into your bank account, say. R is the initial rate. Of course, we want to put this as a decimal, just like we did in the last example. And T is just your time in years. So the best thing to do is to apply this. Remember, we have A equals P times 1 plus R over N to the NT. Okay, your bank account pays 3.6%, in other words, 0.036 annual interest. If you decide to deposit $4,400 in your account, what will your balance be after 2 years if interest is compounded? First of all, they say semi-annually. Semi-annually means 2 times per year. In other words, our N is equal to 2. So let's just do it. A is what we want to find. P was 4,400. 1 plus R, 0.036 over N, which is 2. Our N is 2. Our T is also 2 in this case. And so if you put that in your calculator, you should get $5,906.82. What about if we compound monthly? So that would be 12 times per year. In other words, N is equal to 12. Do the same thing. A equals 4,400. 1 plus 0.036 over 12 in this case. And then we have 12 times 2. Note that the NT is just the total number of times we compound. Since we do 12 times per year times 2 years, it's a total of 24 times. So we have $5,909.97. So clearly we like it if we compound more times. And that's it for this lesson.
Bye.